All right, welcome to Chapter 4, Section 1, Graphing Exponential Functions. So we've been working in quadratic functions for a couple weeks now. So we're going to move to exponential functions, which have just, a little bit of a different shape there. So first off, let's start on this front screen. So the first thing you'll see is a due date. I don't see it on my screen because this is a teacher preview, but you should see it on yours. You'll also see attempts, so you'll see the attempt number you're on out of unlimited. We do not limit the number of times you submit this assignment. You can come in and try it as many times as you would like. The number of questions just tell you how many questions this assignment has. So this particular one has 8. Depending on the section, it'll be anywhere from 1 to 10 questions. Grading policy is best score, so whichever attempt's the best one is the one you keep, and partial credit is enabled. This just lets us know that once we start our homework, we need to finish it, which means submit it before we can do anything else. So once I click start there's a submit assignment button on the bottom of your screen. You won't see it on my screen here, but on the bottom of your screen it's there. And whenever we want to leave this page, we're going to click that submit assignment button. So whether or not we've answered any questions, or if we've only answered a couple questions, or even all of them, whenever it is we want to leave, we click that submit assignment button. It does 2 things. It stops the program from locking us out of every other assignment, and it shows your teacher what you've been working on, because it affects the gradebook once you click that submit assignment button. So definitely make sure you click that. On the side here, we have these 3 tools. So explanation tells you it's going to take the attempt away because it's going to give you the solution to this question. So it's not going to give you the solution and then let you come type in the answers. You'll have to come back in and try that again on another attempt. An example just opens up an example just like what we're looking at, shows you exactly what it wants you to go through and work on here. And then how to type in the answer. Once you're happy with that example, you can close it. You can open up another one if you'd like. You can also message your teacher straight from the screen, and it'll attach the question there. So we know where to come help you. All right. So if we're looking at this one, so we have the function is defined by the following rule. So, number 1, functions, we always call it a rule. It's the equation, but it's the rule of this function. This is what has to happen each time. So with an exponential function, if you notice, we have the exponent as a variable. So that's the exponential part of this, is that the variable is the exponent. And then it says find f of x. So here's f of x equals 6 to the x power for these values here. So what we're going to do is just plug in x just like we would in any other equation. So instead of to the x power, I'm going to have 6 to the negative 2, 6 to the negative 1, 6 to the 0, 6 to the 1, and 6 squared, or to the first power. So with these ones, what we need to remember too is we're going back a little bit and practicing some of these rules for exponents. A negative exponent does not mean a negative number. That is not what it means. It actually means that it's a number smaller than 1. It's a decimal. And what we can do is we can look at that as if it's 6 to the negative 2, we have over 1. What we want to do is move this 6 to the bottom. It actually works that way with the exponent. So I can have 6 over 2, or 6 squared, not over 2, sorry. 6 squared. The 2 becomes positive because now I moved it down where it's supposed to be. So this would also become a decimal if we, divided out 1 divided by 6 squared, which gives us 1 over 36. I don't believe they're going to want us to do that because we would end up rounding. Let me make sure. Because it's divisible by 3, I'm pretty sure. Yep, we'd have to be doing some rounding because it's a repeating decimal. Since this is divisible by 3, I know that's what's going to happen here. So they're going to want us to leave this as 1 over 36, like that. Not turn it into a decimal. So with this guy, we have 6 to the negative 1 over 1. I'm going to move this down to the bottom. So it's going to be 6 to the first power, which is just 1 over 6. Anything to the 0 power is not 0, it's 1. So it doesn't matter how big the number ends up being, it's going to be 1 if we have a 0 power. And then on this one, I have 6 to the first power, which is just 6. And then I have 6 squared, which is 36 for this last one here. So we're just filling out that table a lot like we would do for any other problem. This one just has the exponent, or the variable as the exponent, so it kind of looks a little different. So this next one, now we're going to do the same idea. but we're also going to graph it. So when we're looking at this one, we want to make sure that we get at least 5 points, which it tells us that, and that was the same kind of rule for the quadratics. In order for this graphing feature to work, it needs at least 5 points for it to work. It's not being specific on which 5 points. As long as there's 5 points in the graph, it will graph it for you. So let's go f of x equals 4/5 x. So we're going to just pick some numbers for x. It's not really too big a deal which numbers we choose, as long as they don't end up being too big. So I tend to do like -2, -1, 0, 1, and 2. Let me write that out so that we can actually see each one. Nope. It would help if it was an exponent there. 4/5, like that. 4/5. 4/5. I did not plan this out very well as far as being neat. Sorry about that. I was just trying to write the numbers out. So with this one, and I'll create a little XY table here just so that we can see it. So I'm choosing -2, -1, 0, 1, and 2. We can choose any points we want. One thing we do need to be careful about is exponential functions get very, very small very quickly, or they get very large very quickly. So they grow quick, and we'll get to see the shape here. It's quite literally just kind of a curve, like a very soft L curve. So let's go ahead and work this out. So this one, it would be 4 to the -2 and 5 to the -2. Both of them get it. So we actually want to switch their spots, and we'd have 4 squared over 5 squared, which would be 25 over 16. And I believe we want to just leave that there. We don't want that to be a decimal, but we're going to need to use this point here to do this. So it's going to be -2 and 25 over 16. And I can see that the point is here. I have to click plot point for it to stay. And I can close that and it'll stay there. If I closed it before clicking plot point, it would just disappear. So since this is and it should be up here, not being multiplied. -1, it's 4 to the -1 over 5 to the -1. Remember, we're going to switch these spots. So it's going to be 5/4. So I'm also going to have to use plot a point on that one because that's not necessarily going to work. I can't do in between coordinates. So 5/4 plot. All right, this one, no matter what, it's going to, if I have a 0 exponent, it's going to be 1. So I can definitely do that one if I wanted to on my own, but I'll just go ahead and plot the point here. And then let's see, if I have 1 here, well, that's just going to be 4/5. That's not going to change anything. So 1 and 4/5 plot. And then if I have 2, it's going to be 2 squared and 5 squared. But I don't have to switch their spots. So it's still going to be 16 and 25, but it's going to be 16 over 25. I'm going to plot that point. So now I can see, hopefully we can see they're kind of in a nice line here. So when I plot this, it's going to show me this curve. So let's see if that's good enough, because usually we have this kind of arching up a little faster, but let's see. Yep, that worked perfectly fine. So it doesn't necessarily need to have any points that are up higher. They can all 5 be in a line, and it'll plot it for us based on that curve. Okay, so now we have 1/4, 4 to the x power. All right, so we're going to choose our coordinates again here. -2, -1, 0, 1, 2. I lose my mind a little bit there. So I know if it's going to be 0, this is going to be 4 to the 0 power is 1 times 1/4. I can fill that guy in. It's going to be 1/4. This is -2, so 1/4 times 4 to the -2 is actually 1 over 4 squared. So we have 4 squared, which is 16 times 4. So we have 1 over 64. So 1/64. So you can see this starts to get pretty small pretty quick. Dang it. Go back. There we go. And then for this one, I'm going to have 1/4 times its -1, so that's going to just be 1/4. So that's going to be 1/16. And now I have 1/4 times 4. It would be to the first power, but that's just 4. So this actually ends up being 4 divided by 4. So this ends up being 1. And then 1/4 times 16, because it's 4 squared when I put the 2 in. So I'm going to divide and end up with 4 left over, so I'll end up with 4 here. So let's go ahead and plot a point tool so we can plot some of these points. And I have 1/64, plot, -1, 1/16, plot, 0 and 1/4. So I can kind of see, I can already see that curve. It's kind of going up here. 1, 1, and 2, 4. So that's starting to go up quite a bit sharper now. All of a sudden it was pretty low, and then it's going to go up pretty sharp. So now I can go ahead and connect that, and I can see how quickly all of a sudden it starts to jump up and grow. So this is the idea of an exponential function, is that it kind of flattens out a little bit here, but it shoots up very fast. And the thing with this line is it's never actually going to get to 0. It's never going to get to the x-axis. It's going to get closer and closer and closer. But no matter how small the number I put there, it's always just going to be a fraction. It's never actually going to get to 0. So that's just one thing to remember on this one. And that's called an isotope, which I believe, nope, don't do that. They talk about here. I think they do talk about it here. Doesn't look like they actually talk about the isotope. So that's just, it's the line that it's always approaching but never reaches. So I believe they talk about it at some point here. So go ahead and check that. Yay! Continue. Okay. So we're just going to keep practicing these guys. So x, so I'm going to have x, and y, I don't know why I made that so crazy long, but I did. 2, okay. So if I put a 0 in here, it doesn't matter what the number is, it's going to be 1. So I already know that one. So then 1 to the -2. So this is, I'm squaring both, but I do need to flip them over. So it's going to be 4/1. So it's going to end up just being 4. And then this is to the -1, so I'm going to just flip it over, and it's going to be 2. So it'd be 2/1, or just 2. 1/2 to the first power, well, that's just going to be 1/2. And then 1/2 to the second power, that's going to be 1 squared and 2 squared, so that's going to be 1/4, like that. So they flipped over again. So let's see, I have, and I can't plot all of them, so it says, oh, isotope, so we are going to do that one, and it looks like isotope, but it's isotope. Isotope, I think I said it funny, but it does have an M in there, even though you can't really hear it when we say it. 2, 0 and 1, 1 and 1/2, and 2 and 1/2. So they made this one a little easier, I think, to see, or 1/4, not 1/2. So we can definitely see this one, hopefully a little easier. So when we plot this, make sure you plot 5 points and draw one isotope. Oh, okay. So the isotope, what is always approaching but never going to reach, is going to be that 0 mark. So this fraction will just keep getting smaller and smaller the bigger the numbers we use. So like I could even go like this and say, let's go to the 5th power. So we're jumping kind of dot, dot, dot down here to the 5th power. Well, that would be 1/32. So 1/32. So it would just keep growing and growing, as getting smaller and smaller and smaller, but never actually get to that part there. So that's where we want it to be. So there we go. So we had to place that line that it's approaching before I could actually graph this piece here. All right. Let's see. All right. So for this one, what we're going to look at, we have the graph of the exponential function as shown below. The horizontal asymptote is shown as a dashed line. So we can see the dashed line there. It's showing it to us. But now they want us to do the domain and the range of each function. So usually, it's pretty much true of all of these, that the domain is not going to be limited. I haven't found one yet where it is limited, because that would be pretty difficult for it not to go left and right forever. I can't really picture one that wouldn't be going left and right forever. I don't think that's possible. So the domain is always real numbers, because even though it's going to go kind of slowly this direction, it's still going to the left, and it's going to go to the right forever. So there's no limit there. But for the range, there is a limit. The limit is this line. It can't go above that line. It actually can't even get to the line. So we want to say that y, that's the range, it has to do with y, has to be less than this line, and this line is on -1. It can't reach it. It's never actually going to get there. It's going to get closer and closer and closer and closer to that line, but it's never actually going to reach it. All right. So let's see. For this guy, we get to graph it and then do the domain and the range. So we're going to plot 2 points in the graph of the function and also draw the asymptote. And then, okay, so only 2 points on the line. Interesting. So we only need 2 points. So let's see. Fx minus 2. So, or 4 times x minus 2. So let's go ahead and go with 0. And we have 4 to the -2, which means that we're going to move it to the bottom. So it's going to be 4 over 16, or 1 over 16. So that coordinate was 0 and 1/16. And then let's go with 1. So we'd end up with -1. That's over this, so we'd have 1 over 4. So that's 1 and 4, because we plugged in 0, we plugged in 1. That's why I have the 0 and the 1. And then this is what we received for both of those. So it says graph 2 points on the line. So that's all we have to do, is graph 2 points on the line here. So 0 and 1/16 plot, and 1 and 1/4 plot. Okay, and then I believe, let's see, this guy is never going to reach 0, if I understand correctly what I'm seeing there. So the domain, it'll still go right and left forever, but now what they want us to do is show this with infinity signs. So it's going to go, and we also have to show it with the notation here. So if we take a look, because there's a lot of notation that goes with this. So with this one, we have this graph, and I need to actually click the graph button so we can see it. So this, we can see that it's showing the domain is going to go infinity, negative infinity, and positive infinity. So that's what the sideways 8 means. It's the infinity symbol. So we're just showing that it can go infinity forever. But the range has a limit of 0, and it can go up forever. So we want to show that has a limit on one or the other, moving that piece around. So let's see. Oh, and this is the general one, but so this would just be 3 of x, and then with the -1, it moves it down 1 like that. So it's going to shift it over so that it doesn't have that piece. Let's see. Shift. So it's shifting it down for that one. This one actually might shift over a little, but I don't think that's actually going to matter because it is shifting it over a little bit. It's not as close to the axis, but that's really not going to change any of these pieces. So I have negative, positive, this guy is still going to be the same. It's going to be 0 and infinity up forever. So the bottom, the limit there is 0. It's never going to reach 0. All right. So we're going to do a word problem. Boop, 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 boop. Okay. So just like we did before with the linear equations, we want to look at what is our starting point and what is our change, and that's going to either be decay or growth. So at the beginning of a population study, a city had 250,000, I don't know why I say 2,500, 250,000 people. So this was our starting point. That's how much it had at the beginning of the study. Ever since, the population has grown, so that's growth, of 4.4%. We're going to let t be the number of years, and this is every year, so I'm even going to write every year. So t is going to be the number of years. So instead of every year, we're going to go t, and we're going to let y be the city's population. So that's going to be the total. So what we want to make sure is we understand is that every year it grows 4.4% from what it was before. So I'd have 250,000 times 4.4%. And that would be year 1. Year number 1. Year number 2 would be this same amount times another 4.4%. Because it's the previous year, and then we grow another 4.4%. Year number 3 would be this entire amount times, oops, I was trying to be lazy about it and not write out the whole thing, times another 4.4%. So if you notice, each time I include the last one. So every year there's another 4.4%. So there's 1 in the first year, there's 2 in the second year, because remember this comes down, I was just being a little lazy about it. There's this one that comes down and this second one, so there's 3 of them here. So that has to do with the exponent that's going on there. And that's the number of years. So 1 year I have 1, 2 years I have 2, 3 years I have 3 of them. So we can see how this kind of gets built a little bit. So what we're going to do is the beginning amount times the percentage, and we want to make sure we change this. We don't want 4.4%. We want to go 1, 2, move it back. So we have 0.044 like that. 0.044 to the t, like this. T is the number of years, so remember if I had 1 year, I had 4.4. If I had 2, I had 4.4s. If I had year 3, it was 3 4.4s. In year 4, I'd have 4 of them. So the number of years is the exponent there. That's how many times I'm going to multiply by itself. And this is going to equal y, which is the city's population. So it's kind of similar to how we do the other one where we had the starting point and a change, but this time the growth or the decay is going to be raised to an exponent. It's not going to be multiplied by the exponent. The exponent tells us how many times we're using that growth or decay percentage there. Times 0.044. And that's to the t. All right. Check. Uh-oh. What did I type in wrong? Did it not like my decimal? Zero 0.044 T. Wonder if it doesn't like the decimal. No, that's good there. What am I missing? Well, let's see. What am I missing? I'm missing something here. Oh, darn it. I forgot to add the 1 back. My goodness. That was a silly mistake here. So the 1 here represents the 100% of the 250,000. Otherwise, if we did 250,000 times 4.4%, we'd have 11,000. So that would mean that we're not adding back to the 250,000. I would have 11,000 multiplied by 4.4%. Well, it's not only 11,000 growing. That was an oops on my part. I forgot to add the 100 back in. So it shouldn't be 1.004. We should have a 100% here. It's a growth. We wanted to add that to 100%. So that was just an oopsie. I forgot that little step. So we want to make sure that we add that back. If it was a decay, we'd subtract it from 100 to show that. So we're adding it to 100 each time. So it's 100, in a way, 104.4% growth, if we look at it that way. So it's just an oops. I forgot the 1. But all in all, still okay. So let's see. If we try this again, let's try another one just to see, since I oopsed that one up. All right, so this time we have, at the beginning of a environmental study, a forest covers this much area, so this is our starting point. Since then, it has decreased, so this is a decay. So decay would mean that I'm going to take the 100% that I forgot in that first one, and I'm going to subtract 5.4 from it, so that tells us how much of the forest is left each year. So 94.6% of the forest is left over every year. So 5.4 of it decays, but we have 94.6% of whatever we started with left at the end of each year. So this is what we're going to multiply by, this 94.6%. And it's each year. So remember, that means if I have 1 year, there'd be 94.6% left. The second year, I'd have this entire piece times 94.6%. The third year, I'd have this whole piece times 94.6%. So each year, it adds another 94.6%. So that is where I put my exponent. So that's just another example of that idea. So we have t here, and that's going to equal y. So now let's type that in the correct way. Silly me for getting that 100%. That's what happens when I do too many of these videos in a row. Oop, and I don't want to type in 94%. I want to make sure it's 0.946. I want to type that in as a decimal because Alex also wouldn't like that as a percentage there. So go ahead and check that. Yay! Sorry, I just forgot the 100% on that first attempt there, but that's all right. Mistakes are perfectly fine. We all make mistakes. We just go back and we try again. All right, so now we're going to compare these two. So we're going to work both of these out here just so that we can see which one, for the most part, they want to know which one is either, for x is greater than -6, so after 6, after this bold line, it suggests that f of x is either sometimes, always, or never less than g of x. So we want to decide that. So we need to fill this out. So we can even use the calculator here. So we have 2 to the 32. Sorry, nope. I'm again losing my mind. It was to the 5th power. 2 to the 5th power is 32. So let's go 2 to the 6th power. We get 64. And then we have 2 to the, I'm going to copy this real quick. I don't know if I can. 13. Let's see. Now I can copy it. So 2 to the 13th power, and that's 92. And let's go 14. 16, 3, 8. Oop. 8, 4. And 15. Oh, that's interesting. My phone was reading me a calculator entry. All right, and I wonder, I don't know if I can copy it like that. Oh, I can. Okay, and I'm going to put the commas in here because that's just bugging me. Commas. Okay. All right, so now we're going to do this guy. So we have 4 times 6, and that's going to be to the 3rd power always. So what we're going to be changing is that 6 each time. So if I copy this, so with this one we have 864. So instead of 6 for this one, I'm going to go 13. And 8788. I don't want to copy this one because then if I copy this one, then I'm going to mess up what I've copied and pasted for that formula, and I have to type that in each time. So I'll just type these guys in. The last one, I can definitely do that. I can copy and paste that guy over here. All right, so let's put the commas in, and then let's do our comparing. Okay, so now that we've filled in this table, we're just making a decision. So after this point, after this bold line here, we just want to decide, is f of x always, sometimes, or never bigger than g of x? So it looks like, no matter what, that f of x is bigger. And it gets quite a bit bigger. So it went from 16 to 10. That was, roughly 6,000 more. Now it's 32 and 13. So that's more than double. So quite a bit more than double. So it's always going to be bigger in this case once we do this comparison. Uh-oh. What number do I have wrong? Let's see. I have something wrong. Let's see. 2 to the 6th power. Let's make sure I didn't type one of these guys in wrong, because that's probably what happened. 13, 192, 14, 16, 384, and 15, 32, 7, 6, 8. That looks good. So 4 times 6 to the 3rd power, 864. And then we have 13, 8788, 14, 10, 976, and 15, 1350. Oh, you know why? It's sometimes, because I just realized that the bolded line is even showing me too that it's right here. It's not greater than until after 14. So I just wasn't paying attention. This number is smaller than this number. So sometimes it's going to be always after this point. So let's go ahead and check. All right. So it was just about making sure we're paying attention to those lines there. And I'm not sure if this bolded line is necessarily permanent or if it's moving down, because it almost looks like it moved down again. So that might just be kind of a frame of reference here, but we want to pay attention to this bottom part where we're looking there. All right, so that was section 1. I will see you in section 2.